So let's start. Hi, everybody. My name is Danilo Pau, and it is my pleasure to introduce you these great tinyML talks from Maen Mallah and Roland Müller from Fraunhofer Institute. The title of their speeches is Tools and Methodologies for Edge AI Mixed Signal Inference Accelerators. But before to leave the floor to our excellent speakers, let me remind that these events, as well as many other organized by tinyML Foundation, would be impossible without the great support of the strategic partners. And let me remind who they are. AIZip, Arduino, ARM, BrainChip, Gimpulse, Embed UR, Efficient, Green Waves, Gravity, IMAX, ImageMob, Infineon, Inatera, Not AI, NXP, PNG, PIMIC, Pauling Technology, Qualcomm, Renesas, Schneider Electric, Sensimil, Sony, Silicon Labs, ST Microelectronics, Synaptics, Sentient, and TDK. And apologize if I not pronounced properly any of these names, these great companies. Let me move forward. Being part of tinyML essentially means to be part of the greatest community at worldwide level that federate all the experts and the company and research labs and many more entities, small, medium enterprise in one community which is much concerned, interested on tiny machine learning. And there are two main assets which helps the community to stay alive and to interoperate among different entities. One is the meetup across groups, across countries, 41 countries. So that's the measure of the diffusion at worldwide level, and the LinkedIn tinyML community, which is exchanging continuously information and latest progresses on many aspects of the tinyML technology. It's important to remind that tinyML Foundation is making happen the availability of a huge amount of content, multimedia content, through the YouTube channel. So if you are looking to information specific to tinyML community dimensions, hardware, software, tools, algorithms, and many other subjects, please do refer to the YouTube channel. Subscribe to it if you didn't do it yet, because it's fundamental as assets and to retrieve any information that maybe you missed or you need to refer to. It's important, ultra important, you keep in mind that on late April 22, next year, it will take place the tinyML Research Symposium. This research symposium is unique. It's unique in many senses. First of all, it happens in San Francisco, where you know, the Silicon Valley is close to there, where many entities are placed, where a lot of innovation are happening, and also because it's a unique event. So please do contribute with your outstanding research, and is fully focused on tinyML enabling technology. So it's a unique opportunity for you to contribute. Please do so, and spread also the news around your community, because it's important to be there and to contribute. Another important document that's been produced by the tinyML Foundation is 2023 AGI Technology Report. Is very useful for all practitioners, freshmen, engineers, experts, which are seeking to stay up to date on AGI technologies. And so far has been very successful. And next year there will be a new edition, so the document will be refreshed. But don't miss the opportunity to download it and to have a look at it and to learn from it. Then, so without hesitation, let me introduce Maen Mallah, which is a researcher in the area of embedded AI at the Fraunhofer Institute for Integrated Circuits. He achieved the Bachelor in Telecommunication Engineering in 2014 at the An-Najah National University, Palestine, and his Master in Electrical Engineering in 2018 from Bilkent University, Turkey, with the thesis titled Multiplication-Free Neural Networks. That's a very important topic in tinyML. In March 2018, he joined Fraunhofer as an expert for embedded AI and focusing mainly on energy-efficient neural networks. Main work and interest focus on implementing optimized neural network for edge application, designing special tools required for such a task with a special focus on quantization and fault-aware training. Let me also introduce Roland Müller. Roland achieved his bachelor at the OTH Regensburg in 2017 and master in 2019 at FAU Erlangen, both in electrical engineering. In May 2019, he joined the Department of Integrated Circuits and Systems at Fraunhofer IIS, Erlangen, Germany, where he is working in the field of analog mixed signal design of neural network accelerator and design automation for such circuits. Currently, he is pursuing his PhD. His main research interests include low-power analog mixed signal circuits, neuromorphic computing, and electronic design automation. So thanks a lot to both to be available and for this speech, and I leave you the floor, Maen.
Thanks a lot for the introduction. Let's start our presentation. As was mentioned earlier, me and my colleague Roland will be presenting, but I want to stress out at the beginning that this is a larger team than the two of us. We are just doing the presentation. We have the names of the people who participated in the work, and there are others who helping to support us. There's not enough room to write the names of everyone, but we just want to stress that it's not the work of two people only. First let me take you through the outline of this presentation. We will have some introduction about Fraunhofer, IIS, and our team, and then we will talk briefly about the hardware, so our mixed signal neuromorphic hardware that we developed here at Fraunhofer. And then we will go to the main topic of the presentation, which is the software tools that we need to support the mixed signal neuromorphic hardware. That goes from the training to KPI estimation, mapper, compiler, and hardware generator. And finally, we finish with some characterization and demo, and end with a Q&A. But as mentioned, there will be a Q&A in the middle as well if anyone has a question in the middle. So first, Fraunhofer, for who don't know, is a community of research in Germany, and IIS, Institute for Integrated Circuit, is one of these many institutes for research. The headquarters is in Erlangen, and it is distributed over 11 cities in the southeast of Germany. There are currently more than 1,100 employees focusing on a huge range of products and projects and research fields. But our topic is neuromorphic computing, and this is mainly entitled a lot of different things, but we try to represent them with a few small aspects. We focused on mixed signal and neuromorphic ASICs, and that's for both DNNs and SNNs, so deep neural networks and spiking neural networks. Our talk today is mainly about deep neural networks, but in the works we also have spiking neural network as well. Our belief is that to achieve this ultra-low energy consumption for inference, we need analog multiply and accumulate computation. And we also want to do that in real time, so we want to achieve ultra-low processing time per inference, so we can do fast computation and high data processing. And finally, we should achieve all of that by co-design between hardware and software, and having automated tool chain that achieves all of our target and mainly the accuracy of our neural networks once deployed on the accelerator. With that, let me first introduce briefly our hardware. I will not go into details, but mainly this is the mixed signal architecture that we developed here in-house in Fraunhofer. It's coined as Adelia Generation 2. We support analog and mixed signal processing cores, that's APUs, that communicate using a cyclic bus fabric. You can see on the right, here's just a diagram of the APU of one of them. There are multiple, and each APU does analog in-memory compute for fast and energy efficient multiplication and accumulative operations. Each of these APUs is field programmable to achieve as much flexibility as possible. And finally, with all of this crossbar array and the analog in-memory compute, it's supplemented by low-power ADCs to interface to the digital, where we can achieve the maximum flexibility but keep our efficiency. And the architecture supports different weight and input precision, up to 9 bits for each of these input and weights. So that was the architecture in general. And one of these architectures, at least that we made and fabricated, was a 6-core chip. Was made in the project Andante, and it has 1 kilobyte of instruction memory, network on chip controller, and digital and analog test circuits. Each APU has 256 times 64 synapses, so these are all the connections that we have. Each of these have 3-bit sign precision. Of course, we can combine multiple of these columns to generate higher precision if needed. Each crossbar array has 8K byte distributed SRAM, 8K byte input memory, 8K byte weight memory, and 1K byte instruction memory. And each of them is complemented with 32 low-power ADCs, in addition to shift and add blocks that can do batch normalization. So with this brief introduction of our hardware, we want to now talk about mainly the focus of the tool. Such a hardware, we realized early on, requires a lot of software development that goes into it to achieve high design, fast cycles, and to be able to optimize and train neural network models that run on such a hardware. And for this, we designed our own tool flow that I will present now briefly, but then go into detail of each of these blocks. So we start here at the top in blue with the neural network hardware generator. This is mainly used to generate layout and schematic for our hardware using the description that we provide. Second, we move to a hardware-aware training. This is the training tool that we use to produce a quantized, robust neural network model that runs on our hardware and produces the same accuracy that we see in training an accelerator. That quantized model is then fed to a mapper and compiler tool that generates our compiled program. And this compiled program can immediately then be deployed and run on our hardware using the deployment and runtime API. Finally, all of the workflow is complemented with 2 tools that do architecture exploration and simulation and KPI estimation. Both of these generate metrics and KPI that are very important to the optimization of both our hardware using the system architecture, where we update our architecture, and our neural network models that are run on the accelerator by updating the neural network model details. So let's now maybe dive a bit deeper into each of these tools. First, we have the training part, where we have our hardware-aware training that produces the quantized neural network model, or at least it should be also as well robust. It requires a labeled dataset and a neural network details. So if we go deeper and we explain why we need at least this tool. First, we have the quantization-aware training part, and this is the first step to achieve low energy by reducing the precision we need in our operations. So if we reduce the precision of the weights, inputs, we can achieve higher calculations with less energy required. And neural networks are robust to quantization to a degree, but eventually we need some quantization-aware training to go as low as possible. For this, we mainly use or extend on Provitas, and that does the quantization part. So here I have on the left the torch layer that has weights, inputs, bias, and produces an output. And this is a generic torch layer. What Provitas team did is they produced this layer that injects quantization details into either weights, new inputs, bias, or output. And you can put a quantizer or no quantizer at all, so you can just pass them as floating points. But the torch layer itself is the same layer that can still be run on GPU, can be still trained as normal. Of course, the quantizer has a lot of different parameters that can be set individually for each layer, for each parameter in the network. For example, scale, number of bits. If you want to delay the quantizer for a few iterations of the training, what is the 0 point, and many others that you can set and configure easily. Now, we have used mainly Privitas, extended it a little bit to suit our needs for our hardware when needed, but mostly this is out of the box from an open source library. Then we run into the main issue, or let's say one of the challenges that we have in analog and memory compute, which is the noise and inaccuracy variations mismatch that happen on the hardware. For example, here we show measurements that we took from one of our accelerators where we measure the weight value that it should be stored. So when we want to store a value of, for example, 0, we have a distribution that actually ends up in the storage units in memory from minus 0.2 to 0.2 and so on for all the other weight values. These mismatches can cause the neural network to produce completely wrong values, not as was already designed and integrated. So for this purpose, we introduced fault-aware training, where we take account of this mismatch and faults, the one I showed as an example, but there are other faults, bit error or noise of the actual values of the activations can be introduced in our tool to mimic the behavior of the accelerator of the hardware so that when we actually deploy the tool, the network, we get the same results. And for this, we devised the hardware-aware training layer. It's similar to the previous layer, however, now we can introduce normal quantizer or fault-aware training quantizer or no quantizer at all. And the torch layer is still the same basic torch layer that runs on the GPU and can be trained, can be loaded, and can be stored. Fault-aware training quantizer is an extension of a normal quantizer, so we have the quantizer in the middle that takes the same parameters, can be set individually for each parameter in each layer. But in addition, it has 2 extra steps to do. One is pre-quantize operation and the one is post-quantize operation. So before we quantize the values, we can introduce to them any implementation of any variance we want. And at the same, after the quantization operation, we can introduce any variation we want with any implementation. So to show some results from this tool, we use voice activity detection use case. Here we have an input of log spectrogram, size 13 times 64, and that has an output binary, either voice or no voice. And the network is 5 convolutional layers followed by 2 fully connected layers. We have 25K parameters almost and 1.2 million MAC operations. For such a network, the floating point accuracy we get is 89% in the test dataset. And here we introduce now, or at least I would like to introduce 2 types of hardware variations that we use in this simulation. One is the mismatch of the analog synapses. That's the example I showed above. And here we use relative variation. So the error we introduce is relative to the value of the weight itself. And then we introduce bit error to the values of the ADC in the accumulation. And this we introduce as an absolute variation on top of the actual all the activations we have. And to show the results here, when we train without any hardware variation, so here we have quantization only training, we get 88% accuracy, which is 1% lower than the floating point network. It's pretty good for 8-bit network. However, when we now introduce in our test the hardware variations, our accuracy drops to 50%, and basically the neural network does nothing, it's just randomly guessing a label and getting 50% accuracy. And for this, we see now if we train our neural network with hardware variations, we lose about 5% in accuracy. So from 88, we drop down to 83 because of all of these variations that we introduce, that some of them are significant to really lower the accuracy. However, the gain we get is now when we actually deploy it or test it with the hardware variations, we get 83%. And this we verified in a lot of different stages in software and hardware. So in summary, I would say for hardware-aware training tool is divided into multiple sections. One is quantization-aware training. Here we allow to inject quantization into the PyTorch graph to produce a low memory footprint, and this reduces the energy consumption. Second, we have the fault-aware training part, which is the innovation part from our side, where we can introduce now any variation into the input weights and bias, or even output of any network, of any layer in any network. And this helps to produce a robust network where the accuracy that we get in the training is the same accuracy we get on the inference when we run it on the accelerator. And finally, we have a custom Onyx export to help export all the quantization details that are needed by our toolchain to run the neural network on the accelerator. And the model exchange as well as standard PyTorch, so we still can save the model as a standard PyTorch model with all of these quantization parameters, so we can retrain the model, save it, load it, and export it to other workflows when needed. Second tool or second part of the tool flow I would talk about is the KPI estimation. And this is very important to optimize our neural network models for our accelerator. We found that if you design the correct neural network model, you can get a lot of improvements from the actual accelerators you are running this on. So to be able to do that fast, you want to do some KPI estimation to produce how much, not just accuracy you're getting on the accelerator, but as well how much energy and latency you're getting. And for this, we have now our current KPI estimator that assumes ideal mapping, takes the neural network information, so how many layers we have, and for each layer, the number of MAC operations, number of parameters, and quantization. This detail, in addition to the architecture descriptions, so how many cores we have that we showed in the earlier slides, how many cores we have, how many processing elements are in each core, and what are the SRAMs and global SRAMs we have. All of this is used to calculate using a reference table the actual energy and latency that a network would produce. However, this here assumes ideal mapping, which means we assume each layer or each MAC operation on the hardware will be fully utilized. We can read the data as fast as needed, and everything works ideally. This is in theory not always, or in practice not always right, and that's why we have the mapping aware estimator. So in here, instead of using the neural network information immediately, where we just assume everything runs perfectly, we actually take the mapped neural network. And the mapped neural network is produced by the mapper. We will explain it later in more detail, but in essence, it will contain how the neural network is mapped, or how the load of the neural network is mapped into each of the operations and memory into the hardware. This is converted into an action counts table, so how many actions should be performed to carry out the computation in the map network. This, in cooperation with the architecture description and the reference table, will give us a more accurate estimation of the latency and energy of a neural network. So using this KPI estimator, then we will be able to determine fast, at least the energy and latency that will be consumed by a neural network on our hardware. And this, I would stop for a Q&A, if there are any questions now.
Thanks, Roland. Thanks, Maen, sorry. I don't see any question in the Q&A part. Maybe I can pose some questions in the meanwhile someone posted their questions. Certainly you've shown that the best achieved performance is with fault-aware quantization training. What kind of type of quantizer do you support in your environment? Do you allow variability, linear, nonlinear quantizers, or you have a special focused quantizer in your toolchain?
I would say the quantization, as I said, is mainly part of Brevitas. They support multiple quantizers, so any quantizer that's supported in Brevitas is also supported by hardware training. And you can, at least the most common one they use is, each weight is quantized by itself, but there is no more details. So you can quantize any weight or input to the closest range that you define. And the range can be flexibly defined either by learned parameters or for a range that you actually define by hand.
Okay. Thank you very much, Maen. There are questions appearing. The first is if the KPI estimator is available in somewhere in any form.
Unfortunately, not yet. This is mainly work in progress, as the whole thing is work in progress. We are working currently on a project to publish some of these tools to at least as open source software. At least when that happens, we will notify people, but currently nothing is available yet for the public.
Okay. Second question is how your implementation comparing precision and energy consumption to GPU baseline solutions. Do you have any figures, any comment about that?
We haven't compared at least precision with GPUs, but we are working on benchmarking now, but at least it's not in our roadmap to compare to GPUs. We want to compare to other accelerators that exist in the market, but not GPUs, because the target is very low power edge devices that run on maybe battery. So if you want to imagine, it will not be a GPU, it will be something run on a battery for a few days minimum. That's the target applications for our accelerator, and then we will compare with similar in the same range or slightly higher range.
Yeah. Thanks, Maen. There is also another question, more or less is in the same direction. At least it gives you a little bit of feeling maybe on the importance of benchmarking. There is another person that is asking the benchmarking compared to CPU, GPU again, the tensor processing unit and application processing unit. So you get the feeling a little bit how the community is interesting to compare one solution to the well-known one, even if, as you clearly say, your development is for very low power and resource-constrained devices. Any comments or?
Yeah, I would say benchmarking is also very important for us. We currently are doing the benchmarking itself. We're testing our accelerator versus others. We still don't have yet public numbers that we can release, but it's also very important to us because we want to know where we sit. And at least what we observed is that the high accelerator market, so mobile phones level and higher, is already, at least in our opinion, well developed for. And that's why our target is the lower than that even of mobile phones. And we think there is a gap there, but now we'll show that in numbers, of course, and we are interested in benchmarking and releasing these numbers as soon as possible.
Okay, fine. Next question is if I think is in the framework of continuous learning, if you can retrain, refine the model once deployed.
Sorry, can you repeat again the last part?
I think the next question is related to the topic of continuous learning. So can you retrain the model once it has been deployed?
Currently not. We have plans of future updates of our hardware where we will be able to modify some of the weights at least and increase this retraining refinement on the hardware. But currently the current solution we are working with only does deployment and inference without retraining.
Okay. Thank you. Another question is about quantized model export to NX. Are you exporting the model with quantized operator like QuantConv or using the Q format? Which one would give ideally lower runtime memory footprint?
Not actually sure what Q format is. We looked into QuantConv and Quant fully connected operations that ONNX supports. However, we found they are not suitable for our case because they only support integer 8 and unsigned integer 8 and integer 8. While in our case, we support 3, 5, and 9-bit precision for the weights. And similarly, for the input, we support from 1 to 8-bit precision. And all of these were not possible, at least with the QuantConv and Quant fully connected operations that ONNX currently supports. We are looking to try to find a common solution with everyone, so we can have a standard export, not our own export, but that currently we have just custom Onyx export. We try to keep it as close to possible to Onyx, so that once we reach a common standard with everyone, it would be very fast to change. Or at least that's what we hope.
Okay. Another question is, what techniques are used to optimize the KPI? Is there any optimization step or anything that helps?
Currently, that's not part of our research, but at least what we find important is to be able to produce the KPI estimation, and we use out-of-the-box solutions to optimize genetic algorithms, neural architecture search, where we give it the black boxes we have. So this is the estimator, this is the details of the network that we can specify, but we are not yet working on the neural architecture search part of this optimization. We just use out-of-the-box solutions.
Okay, thank you. Was there a thermal drift in accuracy precision?
Sorry, again?
Was there thermal drift in accuracy precision?
I'm not sure, maybe
I answer that. So I think this is related to the hardware actually, and how the circuits are designed. There's very few variations to temperature. So on accuracy level, it's like plus minus 1%, and therefore I wouldn't consider that really as a drift. So the circuits, all our circuits are designed to work on mismatch and temperature variations.
Okay.
Please let's continue with the presentation, and if there are other questions, we can answer.
Wait a second, Maen. There are other 5 questions in the Q&A session, so please make sure that these answers are answered even later on, because you know the community is very interested on your talk, so it deserves also the merit to get the answers. But definitely it's time to move to Roland's speeches, and so please, Roland, take the floor.
Yes, so thanks, Maen, first of all, for presenting the first part. So up to now, we have most of the things we need for training, and also KPI estimation, but you also have to get to the actual hardware. And the first step, you already heard about it, is mapping the neural network to the hardware. So in this case, we have the quantized neural network model we get from the hardware area training tool. And we also have the system architecture. So how does our chip actually look like? And that contains number of cores, that contains, for example, the memory sizes, all the resolutions we can implement. And that goes then into the mapper. And the mapper actually has the job to distribute the workload onto our chip, such that we get a compiled program which is then executed on the actual hardware. And where is this within the toolchain? So we saw we have the neural network model. Here it's mentioned PyTorch, but it can also be our, most likely it's going to be out from our hardware training tool. Then we have Onyx, which is a custom Onyx, also containing the quantization information. And that then goes into mapper and compiler, and there we get instructions for our custom hardware. So what's inside mapper then? We have that down here, and the first part is just to check, okay, is the data actually in the correct format? So we get the Onyx file, we read it, and we walk through it and see is everything correct? Can that actually be theoretically mapped? That's the first check to give the user a clear info or clear indication, okay, there's something wrong or we can go on. Next step then is parsing the information into a graph. So the neural network will be represented as a graph. And the parser does that by going through the Onyx file, converting the information into something we can use inside the mapper, and then it builds a linked graph to represent the neural network. Next step is analyzing the graph we just created. to understand the data flow, how things are connected and what we actually need on the hardware. And then it gets actually into the mapping step. And what the mapper in there does is creating a map space. And the map space basically contains all kinds of different mappings. So neural networks can be mapped in different ways onto our hardware. We see that on the next slide. And this is a huge map space. So there might be thousands, 10,000s of possible mappings to execute the same neural network on our chip. And this means out of the map space, we then have to select one mapping that suits our use case and our requirements. And that's done by the optimizer. So the optimizer, and that comes also back to KPI estimation. The optimizer takes the mapping information, gives it to the KPI estimation, from where we get the KPIs back. So this might include the latency, throughput, energy consumption, and also how much memory is used. And then the decision is made according to what is the actual target. Should it be energy efficient? Should it be fast? We select one. At least it has to fit onto our hardware, so we have to have enough resources. And that's the optimizer. That's where we can target the mapping of our neural network into certain directions. And finally, the selected mapping then is given to the scheduler, which creates the instructions for our custom hardware. And the main workload is actually there in mapping and optimizing because it's just such a huge map space. And how does this look then? So we got our multi-core accelerator here with the crossbars, and we have one mapping example. So the different layers are mapped in different cores. So we got layer 1 here, layer 2 is then stretched across 2 cores, as well as layer 3, and so on. And then there are some layers which are also in parallel in the cores. And as I said, this has a huge impact on KPIs. And if we, for example, take layer 2, the green one here, in this case, it's mapped such that all the weights are already in our accelerator cores. So we don't have to move those weights from memory to the core and back and exchange them. They stay stationary there. And that, for example, has a huge influence on energy consumption and also throughput, because the reloading of this weight is quite energy consuming task. So if they are stationary, we have less data movement, and therefore we are more energy efficient. And the second thing is, if we reload those weights, because we have to exchange them, this also takes time, so that reduces our throughput. But the advantage of that would be that we might use 2 cores less. So we could build a smaller accelerator and therefore save some silicon area. So there you can see where the impact of mapping actually lies in. And so, to achieve these different mappings, we have to implement different mapping strategies, one for keeping weight stationary, one to optimizing throughput, and one also to optimize the resource usage, or just by to use actually less resources to reduce the silicon area. And in this case, for example, the goal was reducing the data movement and in parallel increasing the usage of our hardware resources. So that's what the mapper does, and that's where we see that it has a huge influence. The next step is then architecture exploration and simulation, and that's even closer to the hardware, because here we want to define how our system should actually look like. So what we have as an input is a system architecture. There might be multiple variants of this, and we have our compiled neural network, and this goes then into architecture exploration and simulation. And what are the goals of these tools? First of all, what we want to do is, before we actually implement the circuits on silicon, we want to see what are the best options. What should be actually implemented, and for that we need a high-level architectural simulation where we can see, okay, what influence do the architectural decisions have on the performance of our future ASIC. And that's divided into two parts. The first thing is architecture structure exploration. So that's where we actually check what different combinations of how we can implement these circuits will influence the behavior. And this might include, for example, how many cores we want to have. Should there be global or local memories? Do we need multiple hierarchies of cache memories? Or what kind of on-chip communication we want to use? So those are the decisions we want to take in structural architecture exploration. And how we do that, and that's all down to making it faster than actually implementing it in hardware or in simulating it. We keep the functionality where it's allowed on a very abstract level. So on some blocks of our circuits, we don't really need the exact modeling of them, we just need a behavioral description. And that leads to a low implementation effort, and therefore we can do this architecture exploration in quite fastly. But still, because we also want to get some KPIs from the whole tool, is that we have to, where it's critical, we have to simulate it timing accurate. So some of the on-chip communications are actually modeled with the accurate timing, but not all of them, and that also improves the simulation speed. And the final point there is we use abstract interfaces, so we don't really implement the interfaces like they would be on hardware again. We model them on an abstract level, and that enables us to exchange some models and actually plug them together and connect them how we want them in the simulation. The other part is then architecture parameter exploration, and there we try to find out what kind of dimensions we need, how big our cores have to be, what should be the memory sizes, or what bus widths we want to use for the on-chip communication. And from all of that, we again get KPIs to see actually how the decisions influence the performance of our circuits. So our solution then contains a heterogeneous system C model. So as I said, some components are just loosely timed, where it's not timing critical. Others, like the interfaces, are then cyclically accurate. We calculate the KPIs in the simulations to see what the effect on latency, power we can estimate from the architecture decision, and everything is driven by setup files, like the architecture configuration, instructions, input data, and hardware metrics to make this all flexible. And all in all, we achieved a high simulation speed by doing that behavioral implementation, and that enables us to do module level verification, system level verification, and we also can verify our mapper and compiler before having the hardware implemented. And so we can optimize KPIs already on architecture level. What are the outcomes? As I said, metrics and KPIs. We get the performance of the neural networks. We get some waveforms where the timing is accurate actually, and we get the visualizations and animation of how the whole chip behaves, which helps us to better understand how, for example, a mapping works. Then the next step is another step closer to the hardware, and that's actually neural network hardware generated tool. And there's the first question, why we actually need this. Why do we need to automate? So we want to automate the design of our neural network accelerators. And that's down to the fact that we build analog mixed signal AI accelerators. And normally, how these circuits are implemented is by doing a manual layout and schematic design. So we have a layout, for example, here of one of our accelerator cores. And normally there's a layout engineer and a schematic engineer, and they create the circuits manually. But in the case of neural networks and accelerators, we have more than 10,000 circuit instances. So in this example, it's 16,000 circuit instances. So it takes a very long time to do all of this manually, and therefore we have a long time to model. So we want to reduce that, and therefore we need automation. The next thing is we want to make our design process a bit more robust. And that's also down to the size and the complexity of the circuits. There are multiple millions of circuit nodes, thousands of pins, and that leads to the situation that there might be errors already in the schematic design and therefore in the layout design. And we can't catch them in simulation because simulating these circuits actually in use case data, we estimated like 100 years or even more. So 100 years simulation time. So we can't catch the errors in simulation on the complete chip level. So what we do, we use the automation, we create small examples which contain the same structure but just smaller. Verify them, those as they are smaller, we can also simulate. And then we can assume if we scale that up, it's still going to be the same circuit structure and therefore it can be correct. So we reduce the possibility of errors. And the final point is the design cycle. So we developed the neural network algorithms and the hardware in parallel, which means we have to react fast to changes on both sides. And therefore we also need the automation. How it works is actually we have a set of standard cells. This is synapse and neuron cells, for example. We feed them into our synthesis flow, where we first of all create multiple configurations. How we could do the schematic layout. They go then into performance estimation. This is also back to the KPI estimation, but more on an analog circuit detailed level. We select the best suiting block for that design. So the best suiting standard cells, and that goes then into synthesis, and finally we try to at least do some simulations to see if we match the requirements. And with that, what we achieved is that from having a neural network and architecture and configuration, in less than half an hour we can actually get the complete circuits. And if we compare that to how long it would have taken us to do the circuits manually. So we estimated it here for 3 different designs, where we had a runtime for the tool of 30 minutes in the first one and 5 minutes in the other tools, and we estimated 1 to 3 months of manual design time. So we greatly reduced the time we need to get our circuits designed, and that helps us in reducing the time to market. Final step then is the runtime API for ASIC characterization and also demonstrating our circuits in a real-world environment. And in this case, what this does is actually executing the neural network on the chip then. So it takes the compiled program and a labeled data set, and that's then fed into the hardware, and we run the neural network. And we have 2 different setups for this. First one is for characterizing the ASICs, and that's in the lab for measurement. And here we have a fully automated test setup, which first of all configures the ASIC on startup and then runs some test patterns for the neural network. And while running the neural network, we measure the power consumption, we log the input data, the output data, and also some analog values. And with that, we can verify that the complete chip works and also the neural network works. And why does this have to be automated? To check all the features on the chip and all the weights, for example, these are it's a very high number of test patterns. So doing that manually wouldn't be possible. That's why we have to automate that to be able to verify completely. And the final stage then is we got everything together. We get a neural network which is quantized and it's robust in regards to the variation we have on our chips. We got that mapped to the ASIC, so we can actually execute it and it performs with good KPIs. We have the hardware there, and then we can put it together into a demonstrator that's shown here on the right side. So in this case, we got our ASIC, and we got a Raspberry Pi and the display, and on that we can run different tests. We can use live voice, so this was voice activity detection, the use case. So in this case, we can run live voice activity detection with a microphone input. We can measure the power consumption, or we can run our data set. to see if the accuracy on that platform actually matches with what we saw in measurement and also in simulation. And that then finally shows, okay, with our chips and the complete toolchain, we can actually execute neural networks in a real-world environment in a robust way. And that's about it, about our toolchain. I got the acknowledgement here for the project where this work was mainly founded in. And then our contact information, so that's my contact information and Maen's contact information. We also included our head of integrated circuits department, Loretta Matteo. She's the main contact person for all the neuromorphic hardware activities. And with that, it's time for another round of questions.
Thanks, Roland, for your great presentation and great talk, as well as the one from Maen. Thanks again. Quick question for you, Roland. Have you explored an architecture that is generic to allow different solutions with a single chip?
Come again?
Have you explored an architecture that is generic to allow different solutions with a single chip?
Different solutions in terms of neural networks or chip implementations?
But it's my interpretation. I think the question is about how flexible is your solution towards maybe, yes, different neural networks.
Yeah, so actually everything is configurable. So we can execute different neural networks with different number of layers, also different quantization values or quantization levels. So everything is actually programmable. The only limitation is the on-chip resources. So there is a limitation in how much memory we have and how fast we can process. But otherwise from that, we can execute quite a few different neural networks. We are a bit limited at the moment in terms of what layers we can do. There are convolutionals, I think dilated convolutions, and fully connected, but we are extending that feature set with every generation of that chip.
Thanks. There is another question which is related to the previous one. Does your solution support reservoir computing and or spiking networks, even as planned?
Spiking networks, both. No, at the moment we are still. We have the first chips now. Spiking actually, with the architecture we shown and the chips we shown, that would be challenging because of the size we decided for the circuits. And that's needed for DNNs, but not really for spiking networks. But we have another track where we actually develop spiking neural network accelerators as well, but they look quite a bit different and they also have their own tool chain. And reservoir computing also not at the moment. So mainly CNNs we can execute, or all kinds of normal DNNs.
Okay, thank you. There is a quite long question. Let me try to understand the core of the question. Do you think that maybe if you come up with a framework tailored to your chip might significantly reduce, if not avoid, some of the challenges you currently face? Since you no longer have to tweak torch to work on your hardware and also take into account the torch behave as you want it to, I believe with a framework tailored for your chip, all you have to do is to add a feature as you go, significantly shortening your developing time. Please enlighten me on this matter, or just a thought from my experience in trying to force TensorFlow Lite to work on some boards. I don't know if it was clear. It was quite long question.
If I understand correctly, I think the question is asking if we do our own framework from scratch, it would solve a lot of the problems we are facing. I think in essence, I would say probably, but the effort to come up with a framework from scratch is way more significant than solving the challenges that we mentioned. I think having Torch as a backbone reduces a lot of the effort of re-implementing everything that we need there, and we just add the solutions we have on top. So I wouldn't think building a framework from scratch is the solution here.
Yes, I agree. And on some points, some of the tools it might be, which are very tailored to the hardware, like our hardware network generator tool, that's completely from scratch, but also using some existing design software. On neural networks, I fully agree. We shouldn't reinvent the wheel here. There are very good tools out there. They can be used, and they should also be used. Simply also for the reason that the industry is already used to using such tools.
Exactly.
And so we also have to support them and support the designers out there bringing their solutions to our hardware.
Yeah.
Okay. Another quick question is, what is the size of each core? Size, I'm not sure what does it mean, in silicon or the internal composition. How many multiply and accumulate operations are possible for each core, I guess?
So each core at the moment has roughly 16,000 multiply and accumulate units, so 16,000 weights. But that's also because we have the tools to scale that, to create that automatically. We can scale it up and down. We can adapt the number of cores. So we are quite free in the one we showed at 16,000 per core, 16,000 2-bit operations.
Any figure in terms of real utilizations of these marks in some use cases or case studies or benchmark of your preferences? How far are you? I'm asking you, how far are you in some benchmarks, in some case study that you tested? How much are you far from the peak utilization in real use cases?
Yeah, this is dependent on how we do the mapping. Utilization on the hardware, we're not that great, but we're also not that bad. So we're somewhere in the middle. But the main goal for what we did till now is lowering the energy consumption, and that comes along with keeping the weight stationary, for example, and that decreases the utilization a bit. But with some changes, we should get up to like 70% utilization or somewhere in these numbers.
Okay. Last but not least question, I think is implementation dependent. If the intermediate outputs in the circuits, in the different stage of the circuits are accessible?
For testing purposes, yes, they are. Not for the application.
Okay. Very good. We are heading toward the end of your great speech. So there are still outstanding questions in the chat. Kindly reminding you to take some time to answer to each of them so that all will be addressed. And thanks again for your speech. I'm going to request the control in order to conclude the presentation with some general information.
Thanks
so
also
thanks again, Maen and Roland.
Thanks to you too for organizing and coordinating.
You should have control now.
Thank you. So thanks again to our speakers. As many others events, also tinyML talks are possible thanks to the great support of the strategic partners. And in particular, let's go through all of them. The executive strategic partners, Qualcomm AI Research, Cynthia. Then the platinum strategic partners, Embedded UR, Sony. The gold strategic partners, ARM, Edge Impulse, Infineon, Innatera, Renesas, ST Microelectronics, Synaptics, and the Silver Strategic Partners, quickly reminding AIZ, Arduino, BrainChip, Efficient, Greenwaves Technologies, Grovity, IMAX, ImageMob, Not AI, NXP, PNG, PIMIC, Pauling Technology, Schneider Electric, Sensimil, Silicon Labs, and UK. So thanks a lot to everybody, especially the speakers and all the attendees. Thanks, Olga, and let's meet again to the next great tinyML. Bye.